Fourier transform of signals. So we find the Fourier transform of continuous time signals. The continuous time non-periodic signal, when we are given with, and if we have to represent to its Fourier representation form, then we have to go for the Fourier transform of that signal, because as it is non-periodic, the Fourier series will not be found or is not present, is not existing for that signal. So the Fourier transform of the signal x of t is what? The Fourier transform of the signal x of t is represented by x of j omega, where j omega is the frequency domain representation. Capital X, j omega and x of t are the time domain and frequency domain representations of each other. Then what will be the equations corresponding to these Fourier equations? Let's see. X of t is equal to what? X of t is our Fourier, is our time domain signal. Its Fourier representation is given by x of t is given by is equal to 1 divided by 2 pi. X of t is the synthesis equation, which is given by 1 divided by 2 pi integration from minus infinity to plus infinity, integration from minus infinity to plus infinity. It would be the x of t it is taken, means it would be x of j omega and those terms. So let's write this one as x of j omega, x of j omega e raised to j, e raised to j omega t, as x of j omega is this d omega. So this is the first equation, to which we call it as the synthesis equation. So this is the synthesis equation. Then another equation will be the corresponding to x of j omega. This x of j omega is equal to integration from minus infinity to plus infinity x of t. It would be e raised to, with x of t always minus j omega t dt. So these are the two equations corresponding to the Fourier transform. So this is referred as the analysis equation. So it is our analysis equation. So Fourier transform we find for the continuous time non-periodic signals, and the equations would be in this fashion. So as the period is not there, fundamental period is not there, and even the frequency is not there, fundamental frequency. So integrations run from minus infinity to plus infinity, and always whenever x of t is involved, there has to be an integration. And even whatever, it is not a summation in case of Fourier transform. Why? Because the Fourier transform of a continuous time signal is also continuous in nature. It is not a discrete in nature. So we have 1 by 2 pi integration from minus infinity to plus infinity. When we find the Fourier transform of particular signals, we'll get to know this integration is nothing but, it is the understanding that, or it is telling us that the output is not discrete in nature, it is continuous. So before going for the problems, let's see the properties, and the properties are important of this both Fourier transform as well as all these Fouriers. This is a DTFT, FT as well as continuous time Fourier series. The properties of all these would be equally important. Let's see the properties of Fourier series. The properties of Fourier series are as follows. So let's see the first property, that is, let's see which all are the properties first. Linearity, time shift, frequency shift, scaling, time differentiation, frequency differentiation, integration, convolution and modulation are the properties. We'll see the proofs of all of them one by one. And Parseval theorem. So up till Parseval's is that for the syllabus. So Parseval theorem is there. Now let's see the linearity property. So what is linearity property? We know weighted sum of input signals should be equal to the weighted sum of output signals. So to prove that one, we need to consider two signals. Let's say x of t and y of t are the two signals, and that Fourier transforms, the Fourier representations of x of t is x of j omega and of y of t is y of j omega. And let's take z of t as the weighted sum of input x of t and b into y of t, the other input, and this should be equal to the a weighted value into the Fourier representation plus the weighted value into the another signal's Fourier representation. So let's write x of j omega is what equation as our analysis equation, and even with respect to y of j omega we'll write these equations. And z of j omega is also given with this. Now we substitute z of t as this one. When we substitute, we know the multiplication is distributive. This e of e raised to e of minus j omega t gets applied to all these terms, and even integration we can apply to both of these terms. So these equations would be in this fashion, and a into this factor, this totally represents x of t e raised to minus j omega t represents x of j omega, and the other one b into this represents b of j omega. So that's the linearity proof. The next one is time shift. When the time shifted version is applied, then what would be the Fourier representation is our next thing. So the Fourier representation would be what way? Let's say x of t and x of j omega are the Fourier and time domain representations. X of t minus t naught, x of t minus t naught is the time shifted version of x of t. So let's substitute this x of t as x of t minus t naught in the equation, analysis equation, and find out what the result we are getting. So whether it is e raised to minus j omega naught t naught, x of j omega. So we can remember these properties with respect to Fourier series also. There when x of t minus t naught is there, it was e raised to minus j k omega naught t naught we were getting, but k is not there here, the rest of the thing. So it would be almost the same. So x of j omega is given by this equation, and to prove this one, let's say we have taken y of t as our signal. Y of t is x of t minus t naught. So let's take y of t minus e raised to j omega t dt. Y of j omega is equal to, now when we write y of t as x of t minus t naught, this remains as it is. We have substituted the value of y of t as x of t minus t naught. When we do that, and we should have only a term here, so we can substitute t minus t naught as anything. It could be even yeah, there is no problem. So take some value for t minus t naught. When we represent this t minus t naught by another value, then let's say it is a, then dt is equal to dA. So x of a, t minus t naught is a. E raised to minus j omega as it is, but this t is given by a plus t naught. We do that representation, and dt is nothing but a dA. When we substitute this e raised to minus j omega t naught will be outside, because x of a e raised to minus j omega a we should have, means whatever is the term here t, that should be there as the exponential, or that should be the multiplication of this exponential minus j omega. So this equation becomes e raised to minus j omega t naught x of, and this integration is nothing but x of j omega. Then frequency shift. So in frequency shift, the same as that of the Fourier series. When there we were applying e raised to some value, there we were applying k naught e raised to j omega k naught we were applying. Now here e raised to j beta we are applying t, and as it is non-periodic, k will not come. So we need to remember these properties in correlation, so that it may be anything. If it is for Fourier series also, we can derive Fourier transform as well as the discrete time Fourier transform. Almost all the properties remain same. So when y of t is equal to e raised to j beta t x of t, y of j omega is equal to what? It has to be x of j omega minus beta in the bracket. So how we get, let's see, we write the equation of x of j omega. Let's write the equation of x of j omega. Once we write this equation, now the next point is we write it for y of j omega also, because we need to substitute. Then let's substitute y of t as e raised to j beta t x of t, because our y of t is the shifted version, e raised to minus j omega t dt. Now here what can be done? We need to combine these exponential terms. When we combine these exponential terms, we get x of t e raised to minus j omega, e raised to minus j, let's take outside, so we can write omega minus beta into t. So again this represents the same equation. And now if we see what we should have, x of t e raised to minus j some factor into this t should be there, and whatever is there except that minus j and t, of that Fourier representation is x of j omega, if omega is only there, but here omega minus beta is there, so x of j omega minus beta, it is there we were getting like x of k minus k naught. Now here it is omega minus beta, because beta we have applied. The next one is the scaling property. The scaling, we know the scaled version of the signal, either it can be an expanded version or it would be a compressed version. So let's say x of t is a signal and whose Fourier transform is x of j omega, and similarly let's consider y of t as the scaled version of x of t signal and whose Fourier transform has to be in this way. Let's see how does this arises, this we can obtain. So we write the Fourier transform equation corresponding to x of t, and similarly for y of t, y of j omega. Then in y of j omega equation, the y of t is the scaled version of x of t that we substitute. Now we consider that a is greater, the positive, a is greater than 0. Then as a is greater than 0, then let's say at, we should have a single letter as we already know. So we can take up some letter representing this a into t. So here tau is there, let's say is equal to tau. At is equal to tau. Let's do the differentiation of this. Dt is equal to this d tau, and this a into dt, it has to be, it is taken on the other side, this 1 by e. Now when we write this y of j omega equation, it becomes x of tau e raised to minus j omega, it has to be. Then we know after scaling the signal e raised to j minus j omega, omega will turn as because if we have the signal in this way, if it is scaled, then the new signal would be in this way, which will be either the compressed or expanded version depending upon the value of A. So its value would be, let's say it is omega, let's say -1 and +1. So it would be 1 by A minus 1 by A and plus 1 by A. So after scaling, the signal gets compressed or expanded. So we need to consider that effect. So the value becomes x of tau minus j omega by A tau. It has to be. So by equations, it is minus j as omega as it is. Now t is replaced by tau, means this t is written as tau by A d tau. And as this dt is equal to 1 by A d tau, so by substituting those all, we are getting this equation. Then y of j omega is equal to 1 by A. So this all represents, now x of tau is there, the same tau is there, and minus j. We have that same equation, but then except this minus j and tau, the other term is omega by A. So we need to write x of j omega into whatever is except minus j and the variable which is there here. So it is omega by A. The same thing when A is less than 0, we'll be having minus 80 as term, and when we do the substitution, we are getting y of j omega is 1 by A x of j omega by A. So by combining those two, when A is greater than 0 and A is less than 0, even we can write 1 by the magnitude of A x of j omega by A. Then the next one is time differentiation. Again, same as that of the Fourier series. We consider x of t and x of j omega, and in proving this, we'll be considering synthesis equation rather than the analysis equation. So let's consider the synthesis equation and differentiate it with respect to t, because we need to have d by dt of x of t. So the d by dt of this all, here only differentiation is with respect to dt. The term would be e raised to j omega t. So once we do the differentiation of this, 1 by 2 pi is independent, integration from minus infinity to plus infinity. Then x of j omega, differentiation, when it is applied to an individual term, it becomes a partial derivative, dou by dou t of e raised to j omega t. We know dou by dou t of e raised to j omega t is j omega into e raised to j omega t into d omega. When we rearrange these terms, we are getting 1 by 2 pi, integration from minus infinity to plus infinity. So it is x of j omega e raised to j omega t. This is d omega as it is. This j omega, we are writing it here. So it is nothing but the same one, so which we were supposed to. It is j omega into x of j omega, and this term x of j omega is equal to, by comparing this equation, that x of t is equal to this, we have the equation. So d by dt of this x of t would be, we are having that another term j omega here. So d by dt of x of t, as we did in the Fourier transform, it is j omega into x of j omega. Then frequency domain differentiation is the new property in case of, so frequency domain differentiation is not there in Fourier series. In case of Fourier series, it is there in Fourier transform. So when we go for frequency domain differentiation, so we consider this equation, then minus j into t x of t, the Fourier transform of this has to be dx of j omega by d omega. So for this, we consider x of j omega equation. So it is our analysis equation. When we go for its differentiation, then differentiation happens with respect to omega. So d by d omega of x of j omega is equal to d by d omega of this. When we do this differentiation of this equation, only omega term has to be differentiated. So integration will come outside x of t, this partial derivative of e raised to minus j omega t. Same, the properties time domain and frequency domain differentiations are just x of t is considered in time domain, x of j omega is considered in the frequency domain. So the differentiation of e raised to minus j omega t is minus e raised to minus j omega t. This gets multiplied with minus j into t because it is with respect to omega. There it was with respect to t, so it was j omega. So we can write this one as minus jt x of t e raised to minus j omega t, and again by comparison we can write minus j into t x of t is the value of d by d omega of x of j omega. So this will be when minus j into t x of t is there, it is the differentiation in the frequency domain. So this value, when it is getting with the, like when we do the differentiation in the frequency domain, it gets multiplied by minus j into t. X of t is getting multiplied with this value in the time domain. Next property is the integration property. The integration property says that integration from minus infinity to t x of tau d tau, where x of t and x of j omega are the Fourier and time domain pairs, then the Fourier transform of this x of tau d tau is x of j omega divided by j omega plus pi into x of j0, when j0 means when the value of x of j omega when omega is 0 into d omega. So we can see these in properties. The proof of this one is there in one of the problems. We can solve that problem later. The next one is the convolution. Convolution is x of t star y of t. The same thing is done here, that we need to consider the analysis equation, and in the analysis equation z of t we need to write, and x of t and y of t are required, and z of t is convolution we write, then we expand this x of t star y of t. We know expansion of convolution, that is integration x of tau y of t minus tau d tau, and this e raised to minus j omega t dt. And we do the interchanging of these integrations, x of tau and the integration y of tau t minus tau e raised to minus j omega t, and we have to replace this t minus tau with another letter. Let's take the another one variable as a, and with respect to a, when we do, it is dt is equal to dA, and the same equation wherein y of a it would be, and e raised to minus j omega as it is, but this t becomes a plus tau, and this d tau dt is equal to dA, and this d tau as it is. And after rearranging we get it is multiplication. So it is clear that convolution in the time domain is nothing but multiplication in the frequency domain. X of t star y of t is nothing but x of j omega into y of j omega, which makes the convolution just multiplication in the frequency domain. Then is modulation, the similar thing. The product of signals is nothing but convolution of the signals we are proving, and we consider two signals for all these convolutions as well as for modulation, and x of t and y of t signals Fourier representations are taken. Z of j omega is equal to this equation, and z of t is nothing but the product of these two. Now here in this, to simplify this one, we have to expand one of the signal. So x of t is expansion. We know x of t is nothing but 1 by 2 pi integration from minus infinity to plus infinity x of j omega e raised to j omega t. When we do the substitution of that, now this equation changes as x of t is replaced with this equation, y of t is as it is, e raised to minus j omega t dt. So we have to go for rearranging. This 1 by 2 pi will be as it is, integrations x of j beta, it is, as omega is already involved in our equations, omega is already used, so omega will be, instead of j omega we are using, so this x of t cannot be expanded as this 1 by 2 pi integration from minus infinity to plus infinity. X of again j omega we should not write, so we are taking this beta letter, and e raised to j, the same letter we have to use. So this equation and the same variable differentiation, d omega in place of that d beta, y of t e raised to minus j omega t dt. So with this we have to simplify this all, so that we can write it in the form of that convolution equation, expansion. So y 1 by 2 pi, this x of j beta, it is nowhere related. Beta is not like differentiation. This integration will take first, and then this integration is with respect to t. So integration y of t, it is e raised to, now by combining these two we can write it as minus j omega minus beta t, and the same can be written as, this expansion is nothing but y of j omega minus beta by the synthesis, by the analysis equation. So we can write this way, so which is nothing but, it is just in the form x of tau or x of tau y of t minus tau, in that fashion it is. So we write it as the convolution signal. So it is just, if we consider j beta as a single letter, let's consider it as L, then it is x of L y of this variable omega minus, which is just like tau, because omega is playing the same role as t here. Then it is that main variable minus that j beta is nothing but L, so which resembles the convolution equation. Then the next one is Parseval's theorem. We all are familiar with this Parseval's theorem. So it is, if x of t and x of j omega are the time domain and frequency domain pairs, then integration from minus infinity to plus infinity, this x of t square dt is equal to 1 by 2 pi integration from minus infinity to plus infinity x of j omega, the magnitude will square t omega, and the proof of this one goes with E is equal to, we know the energy signal, here we consider the complex conjugate, we have done it in case of Fourier series, we do the same thing, and this x star of t is expanded, which will be 1 by 2 pi x star of j omega, as it is a star, even though the x of t is having the plus sign, as it is the complex conjugate, it will have a minus sign, d omega. So the equation turns to this value. So x of star of j omega, we'll take it outside, x of t e raised to minus j omega t is nothing but x of j omega itself, and which is nothing but the magnitude, so which proves this property. So these all are the important properties of Fourier transform, and even the next one is Fourier discrete time Fourier transform. So we need to look at those equations and all. So in the next video we'll see the problems related to this Fourier transform.